So in this video, we're going to recap truss analysis. This includes the method of joints, method of sections, zero force members, and also whether members are in tension or compression. So we'll start with method of joints and the general solution process. So the first thing that you're going to want to do is draw the overall free body diagram of your truss. So this includes simplifying your supports into their equivalent reaction forces. Once you've done that, you should be able to identify any zero force members if you have them, and I'll go through in a little bit more detail further along in this video about identifying those zero force members. So the next step that you can take is to solve for reaction forces. However, I have to note that this is not always necessary. It's dependent on what your structure actually looks like and where the supports are located. So yeah, it's very question specific as to whether you actually need to do this. The next step then is to isolate each joint one by one until all the forces that you're interested in have been found. So I have a couple of tips for this. One of them is that you need to select joints that have a maximum of 2 unknowns. The reason that you're limited to 2 unknowns is because you've only got 2 equilibrium equations which are going to be useful to you. You have that the sum of the forces in the x direction will need to be 0, and you also have that the sum of the forces in the y direction will be equal to 0. The reason that you can't use sum of moments to be 0 is, although it's true, if you separate a joint and have a bunch of forces acting on that joint, they're all going to be acting through your point of interest. So when you sum your moments about this point, let's call it P, to be equal to 0, since everything is acting through it, they're not going to create a moment and you're going to get 0 equals 0. So it's not very useful to you. So I guess the main trick here is with method of joints is that you need to be a little bit strategic in which joints you analyze in which order. You need to move across your truss so that you're selecting joints that only have a maximum of 2 unknowns. Otherwise it's just not solvable. So that's pretty much it for method of joints, and there's a couple of examples in the future videos for you to have a look at there. Alright, so the next topic that we have is method of sections, and again I have a method that we can apply for solving these questions. So it starts off almost identical, in fact identical to the previous question, or method I should say, and that's that you want to start with drawing your free body diagram, simplifying all your reactions onto the free body diagram. And once you've done that, you want to identify if you have any zero force members in your truss, because this is going to make your analysis a little bit easier. The next thing is that you can solve for the reaction forces, and again this is not always necessary. It is dependent on your structure and where your supports are located, as well as what I guess members you're interested in finding the forces in. Once you've done that, this is where it differs. You need to cut your truss, and it needs to be through a maximum of 3 unknown members. Okay, again we have an issue where if you cut through more than 3 members, you can't solve it. It becomes indeterminate, so that's not very good. So you need to make sure that you limit yourself to a maximum of 3 unknown members, and I should clarify this, unknown members. If you know what they are, then it's fine. The other point that I need to make is that the truss must be completely separated. Okay, into 2 parts, 2 distinct parts. It can't be still joined in one particular place, otherwise this isn't going to work. Alright, so once we've cut our truss into 2 parts, we need to just keep one of them. So you can select just one side, and you need to redraw the free body diagram with the exposed forces. Okay, so say we have a truss like this, I don't know, whatever, and we make a cut through here. When we redraw it, say we take the left hand side, we need to redraw it with the exposed members. So we're going to have an exposed one here, an exposed one here, and an exposed one here. So 3 different exposed members, and I'm going to recommend that you draw your members in tension. Okay, so as we'll discuss in a second when we get a bit further down, tension just means that they're pulling away from the joint that they're attached to. If you do this, you know that anything that comes out negative is going to be a compression member. But it doesn't really matter. This is just, I guess, what the kind of convention is. So the last point is that you can solve them with your equilibrium equations. You're able to use all three. So sum of forces in X, sum of forces in Y, and sum of moments about whatever point you want has to be equal to 0. And this time the moment equation is useful because you have things acting at different locations. Not everything's acting through the same point. Alright, so that pretty much concludes the discussion of method of sections. So I guess just a point to add on which method you would probably choose in which situation. So most of the time, if you're asked to find every single member in a truss, probably what you're going to want to do is just do method of joints, because that is going to make sure that you pick up every single member within your truss. And it's probably, the most efficient way if you're looking for every single member. When you would apply method of sections is probably when you're only interested in what a couple of members' force actually is. The advantage of method of sections is that you don't have to solve for every single member in the truss, and it's especially useful if you want to find the force of a member that's like in toward the center of your truss. It means that you don't need to do a whole heap of analysis to find it. So that's the distinction between the methods. Joints, use it if you need to find every single member in your truss. Sections, use it if you're only interested in a couple. Alright, so I'll move on. And the next thing that we're going to discuss is zero force members. So we have two different rules for identifying zero force members. Now the first one is that if we only have two members joining at a node and there are no external forces at that node, then both of these members are going to be zero force. So I've given an example of a truss here where we can actually apply this rule. So what we're looking for is places where we only have two members joining at a node and no external forces applied. So here is an example of two forces coming together at a node and we have no external forces applied. So that's going to be an example of having two zero force members here. I guess the other place that we have two members coming together is down here. However, if you were to draw your free body diagram, you would need to simplify this to be a horizontal and a vertical force through the pin. Same with this one actually. But what you would find is that since you've simplified this now, your support that is, you've now got externally applied forces onto your truss. So this no longer fits this rule because you have externally applied forces and you need none to apply the rule. So the answer to this would be that both this one and this one are zero force members. Okay. So the second rule that we have for zero force members, it's if we have three members joining at a node and two are collinear, so that means that they're in a straight line, then the third member is going to be zero force. And again, we need to have no external loads applied at the node or the joint. So we can apply the rule onto this truss as well and see what we can find. So we're looking for places where we have three members coming together and two of them form a straight line. So this would be an example of where that rule comes true. So we have three members at this node coming together, two of them are in a straight line. So this third one here is going to represent a zero force member. If we look down at the bottom here as well, we could have applied it at this node as well. Again, we have three coming together, two are in a straight line, so the third one that comes out is zero force. So we could have identified this as zero force from either of those members. So that's all there is for those two rules for identifying your zero force members. So moving on, a couple of extra points. So often the question then becomes, why do we even have zero force members in our truss if they're taking zero force? And there's a couple of different reasons for it. So the first one is that we have different loading configurations. So usually for the questions that we're solving, we're only going to be looking at one particular loading configuration. But if you have like a bridge or something, you might have multiple different loads. So in one instance, you might have force out here. In another instance, you might have force on a different part of the bridge. So I guess accounting for those different loading configurations means that sometimes a member will be zero force in one configuration, but then it will be taking a load in a different configuration. The next point that I have there is buckling of compression members. So buckling is an issue when you have very long and thin members and they're in compressions. They're being pushed on at either end. So in this case, you would expect that if it's a very long and thin member, it's going to buckle out of shape. Okay. Now, the tendency to buckle is dependent on the length of the member. So the longer the member, the higher the tendency to buckle. So sometimes what people can do is brace their member so that if you have, I don't know, something here in between, let's say we have two members that are in compression. All right, if we pin it here and here with some other member, essentially what we've done is we've halved the length of the member. So there's going to be like a force in here as well on the members. So yeah, I guess the point is if you want to reduce the chance of a compression member buckling, you can put in a zero force member that's not going to take any load, but it will reduce the tendency of the ones around it in compression to buckle. The last thing that we have is redundancy, and this kind of ties back to the different loading configurations. So again, if we have some kind of redundancy in our system, if one of the members breaks, another member, which may have previously been zero force, will take up some of that load. So again, another reason to have a zero force member. Alright, so the very last thing that we have to talk about is tension or compression members in our truss. And in truss analysis, we plot the force of the member onto the joint. Okay, so what that means is that a tension member looks like this when it's put with its two forces. A compression member looks like this when you put both forces on it. So if you look at this picture down here, the red arrows are probably what you generally picture in your head for a member being in tension. It's being pulled on either end. But these red arrows are the force of the joint onto the member. The black arrows, which are the ones that we're drawing for truss analysis, are the force of the member onto the joint. So that's the differentiation here. So all you need to remember is that a tension member, your arrows need to point away from the joint. For a compression member, your arrows need to point onto the joint. Alright, so I think that's everything for our recap of truss analysis. There's going to be multiple different examples applying all this content, so take a look at those if you want further clarification on these topics.